In this video, we're going to discuss the conical pendulum in more detail. In the previous video, we had considered the conical pendulum, specifically the angular momentum of it, when the angular momentum is taken about point C. Now we want to do in this video is consider the angular momentum of the system when the angular momentum is taken about point Q. And then we'll compare and contrast the results of that with what we obtained back in video, I think it was number 26 in this series on analytical mechanics. The playlist for all the videos is at the website digital-university.org. Okay, so here we want to take the angular momentum of our system with respect to the point Q. Now we know in general that the angular momentum with respect to some point, say P, that is equal to some position vector for that point P, then take the cross product of it with the momentum at that point. Well, here we are doing it now with Q, and the object is down here. Now, as we discussed in the previous video, there are two forces on the object, gravity pulling it straight down, and then there's the tension in the rope. Now, when we're taking the angular momentum with respect to Q, then the position vector, of course, is just L, the length of the string, and it's pointing down in this direction. So here for our problem, LQ equals the length of the string pointing downward cross mv, the momentum. Now here we have to think about what is happening. The particle is going around the circle like this, so right at this point here, that tangential velocity v, it's coming right straight at us. It would look something like this. Here's L, the object is here, and then it's going around the circle, coming around like this, so that the tangential velocity vector will be coming right out of the board at us. So here, let's just first of all consider what would be the direction of the angular velocity, or the angular momentum. So we have L, the length of the string goes like this, and then right here at this point, the velocity is coming right at us. So it'll be coming right out of the board like this. Well, now when we take our cross product, we have to have the vectors at head to head, so it'd be like this. So this would be the velocity vector. That dot means it's coming right out at us, and we want to take this cross product. This is L, the string going down to the object, and here's the velocity vector v coming out of the board like this. So if we take this cross product, we want to wrap L into v, so our thumb is pointing outward like this. So the angular momentum is going out in this direction like this, perpendicular to L and perpendicular to the velocity vector v coming right out of the board. Now, over here on this side, the particle is going around the circle. Here, the velocity vector is going right into the board. So now we have the situation where L is like this, and the velocity vector, that's going pointing right into the board. And of course, he would have it up here at head-to-head to take the cross product. Remember, when we're taking the cross product of two vectors, A cross B, we have to have the vectors aligned head-to-head. So the velocity vector is down here at the end of L going into the board. We position it up here so it's head-to-head, and then the X means it's going right into the board. So this is a little bit more difficult to visualize, but imagine now we had a vector pointing right straight into the board. Then if we wanted to determine the direction of the cross product, we have to take our fingers for L and wrap it into that vector pointing into the board. The thumb was pointing outward. So for here, the angular momentum is going out in this direction. Again, perpendicular to L and perpendicular to that tangential velocity vector. Here the velocity vector is pointing right straight into the board. Here the particle is going around like this. Here it's pointing right out of the board, the velocity vector. Here it's pointing right into the board. Here the angular momentum is pointing in this direction with respect to Q. Here it's pointing in this direction with respect to Q. So we see that the direction of the angular momentum taken with respect to Q, that changes as the particle is moving about the circle. Now remember in the previous video when we were taking the angular momentum with respect to point C, that angular momentum vector had constant direction. It was always pointing up. Now when we take the angular momentum with respect to point Q, we see that the angular momentum vector is changing in direction as we go about the circle. Here it's pointing this way, here it's pointing this way. In every case, of course, it is perpendicular to the tangential velocity and to the string L, here and everywhere else on the circle, for that matter. Now, what about the magnitude of the angular momentum with respect to Q? So angular momentum with respect to Q is L cross mv. So its magnitude will be the magnitude of the length of the string, that's just L, times mv, times the sine of the angle theta between the string and the tangential velocity v. That angle is 90 degrees, and to understand why, we have to consider a different diagram. So let's look at this system. Here we have sort of an upside down conical pendulum, but we have a particle moving in a circle of radius r. Then we have some point back here, and then from this point it always goes out to some point on the circle of length L. So if we say the particle, say, is going around the circle with an angular velocity in this direction, that angular velocity also is a vector, and the direction of that vector is found by wrapping our circles in the direction of the angular velocity. It's going wrapping around like this, so the angular velocity vector points upward, which we have indicated like this. Now the linear velocity, or the tangential velocity, that of course is the radius of the circle times the magnitude of the angular velocity, omega. Now what we want to show is that when we have the angular, not just the angular velocity vector pointing up in this direction, and we have L if we take the cross product of omega cross L, what is that? Well, that's the magnitude of the angular velocity, omega, the magnitude of this vector L, which is just L, times the sine of the theta, the sine of the angle between them, which is theta. But L times the sine of theta is the magnitude of the radius vector for the circle, r. So this is just r, and we get omega r. So what we're showing is that V is equal to the cross product of omega cross L. So the tangential velocity V, it's always going to be perpendicular to the radius vector for the circle, and it's perpendicular to L. So if we turn this upside down to get a conical pendulum, here's the angular velocity perpendicular to the radius for the circle, but it is also perpendicular to L, which is our rope where the mass is suspended from. So here it shows then that the velocity vector V is perpendicular to L, the rope for our conical pendulum. So this angle is 90 degrees. So the magnitude of the angular velocity with respect to Q is just L m v. And of course, L is constant, the mass is constant, and we're taking both the circle at a constant angular velocity, so of course V is constant. So what we know then is that for the angular velocity, or the angular momentum with respect to point Q, it changes direction, as we saw in these two positions, but of course it changes direction in every position along the circle, but its magnitude is constant. Now remember in the previous video, when we considered the angular momentum with respect to point C, its magnitude was r m v. And that always had a constant direction. It was always pointing in the positive z-axis direction. So we see that LQ, which is this, its magnitude is greater than this because r, that's L times the sine of theta. R is L times the sine of that angle theta. So the magnitude of LQ, which is this, is greater than the magnitude of LC, but here the angular momentum is conserved. It has constant magnitude and constant direction. Here it has constant magnitude, but its direction is continually changing. So in the last video, when we were considering angular momentum with respect to point C, that was conserved. And we found that indeed the torque about C, that was 0. Here, with respect to Q, this is changing. Its magnitude is constant, it's LmV, but its direction is always changing. So this is not 0. So that means then that the torque taken about point Q, that should not be 0. So let's see if we can determine what the torque is when we consider it about point Q. So here's our system. here is point Q, here's the rope, there's the mass, and pulling weight straight down is gravity, mg. Now remember from the previous video that we considered all the forces acting on the mass. There was gravity, plus there was the tension in the rope. But the tension in the rope is felt all the way through the rope, from here all the way through point Q. So that does not factor in to the torque. Remember, when we consider a torque, the general expression is R cross F, where we have some position vector, then at the end of that position vector, that's where the force is applied. Well, for the rope, the tension is throughout the rope. So that's not part of the torque. With respect to point Q, of course, involves the rope of length L. What does factor in is mg. So the torque with respect to point Q is going to be, the position vector is now L, the length of the string, cross mg. And that's going to be the magnitude of the string, which is just L, times mg, times the sine of the angle between them. So here is the rope, here is gravity pulling straight down. It's going to be this big angle here. When we look at it, of course this is 90 degrees, so the smaller angle here is going to be 90 minus theta. This angle is 90, so this big angle is going to be 90 plus 90 minus theta. It's going to be 180 minus theta. So the magnitude of the torque is going to be Lmg times the sine of pi minus theta, but that's just the same as the sine of theta. So the magnitude of the torque is Lmg times the sine of theta, but again remember, L times the sine of theta, that's just the radius for the circle, r. So that is Rmg. So we've determined that indeed the torque taken about Q is not 0. In fact, it equals Rmg. Now, this video is getting a little bit long. I think we'll stop it at this point. But we have to consider, now we know the magnitude of the torque. What is the direction of the torque about Q? And here's where it's going to get a little bit more complicated. So let's consider that question in the next video. What we've established so far is that when we take the angular momentum about point Q, its magnitude is Lmv, and it changes direction. In the last video, when we considered LC, that was Rmv. R is L times the sine of theta, so this is less than this, and this had constant direction. It never changed. It was always pointing straight up along the positive z-axis. Since this is a constant magnitude, but it does change direction, then that means its derivative is not 0 for here for LQ. That means its torque should not be 0, and indeed it is Rmg as we just calculated. But now we have to consider, for the next video, what is the direction of the torque, and how does that relate to the direction of the angular momentum taken about Q. So let's consider that in the next video, and we're going to get some surprising insights when we do that.